So in 2.8, we're going to look at one-to-one and inverse functions. So we'll start with this one-to-one function idea. So a function is one-to-one if no two inputs give the same output. So we have this horizontal line test. So most of us are used to the vertical line test, which tells us if a relation is a function. And so the horizontal line test tells us if a function is one-to-one. So in the left picture here, you could see that that is one-to-one because that horizontal line only intersects the graph once. So that would be a one-to-one function. Now, if we look at x squared without that domain restriction here, we can see that there's intersection points here and here, here and here. So the horizontal line is intersecting in each of those places twice. So that would not be a one-to-one function. So visually, that is what a one-to-one function would look like. Okay, in this example, we're going to show that a function is one-to-one. So the way that we do these is a little bit strange, but we're going to suppose there are numbers x sub 1 and x sub 2 such that f of x sub 1 equals f of x sub 2. So essentially, we're going to take x sub 1 and x sub 2 and plug these in to 3x plus 4 and see what happens. So let's just do that. So this would be 3 times x sub 1 plus 4 equals 3 times x sub 2 plus 4. And then we go through this, and this seems like a really useless operation, but we'll talk about it at the end here. So this would be 3x sub 1 equals 3x sub 2, if we subtract that 4, and then we divide by 3. So x sub 1 equals x sub 2. So that tells us that the function is one-to-one. So if x sub 1 is equal to x sub 2, that means that those two values are the same number. So we tried to choose a value that had the same y output, and we said they were different because one was x sub 1 and then one's x sub 2. But it turns out as we go through that operation that they are in fact the same number. Therefore, the function is one-to-one. And there are just a few examples that deal with this. So you won't have to do that a lot because it's really the same thing every time. Okay, so the definition of the inverse function, or definition of the inverse of a function. So let f be a one-to-one function with domain A and range B. Then its inverse function has domain B and range A and is defined by f inverse of y is x, and that implies that f of x is y for any y and b. So again, these definitions are always, unless you're used to reading math, they're just confusing when you read them. And then they give you this Venn diagram with A and B, which I never liked. So in English, this says an inverse will give back its input when applied to an output. So here's an example. I mean, these are really simple. If you have a function where you plug a 5 in and it gives you a 2 out, then the inverse, if you were to say f inverse of 2, you would now get a 5 out. So what was once the input, which was 5, is now the output of the inverse function. And what was once the output of f, which is 2, is now your input of your inverse. So all that says is that x and y swap positions. So x and y are just swapping places in an inverse function. So the inverse function property, so it's a cancellation property. So if you plug a function into the inverse function, you'll get an x out. And if you plug an inverse into a function, you're going to get an x out. So if you have two functions and you plug one into the other and the other into the one, and they give you an x, then they are inverses. So verify that f of x equals x cubed and g of x equals x to the 1/3 are inverses of one another. So again, the language kind of gets in the way of a really simple idea. So f of g of x means we're going to take the g function and plug it into x cubed. So we have x cubed, and we're plugging in g, which is x to the 1/3. Well, this gives us the number, or the letter x out. Now, if we do that again, but the other way, so we plug f of x into the g function, we're going to take the g function as our outside function, and we plug in the x to the third, and then we apply that exponent. So it's x to the third raised to the 1/3 is x to the 1. So since we got this, x out of both of those by plugging them into one another, that tells us that f and g are inverses. Okay, so here's the bulk of what we work with inverses comes down to this, how to find it. So it's a really simple process. Write y equals f of x, solve the equation for x in terms of y, and then swap x and y. So I have this function 2x plus 1. So y equals 2x plus 1. That's step 1. Done. Solve this equation for x in terms of y. Okay, well, let's subtract 1. So this would be y minus 1 equals 2x. Divide by 2. Okay, and now we're going to swap x and y. So I'm actually going to switch sides too here. So I'm going to say y equals x minus 1 over 2. So f inverse of x is x minus 1 over 2. And if we were to plug in, f of x into f inverse of x, they would cancel everything but the x. So this is the inverse. So we'll do another one like that. Okay, this one's a little bit, looks more complicated. We're going to find the inverse of it. So it's already set to y equals, so that's like step 1. And then we're going to multiply and solve this for x. So we multiply both sides by 4. So we get 4y equals 3x cubed minus 2. We add 2 to both sides. Okay, divide by 3. And you'll notice I'm skipping some steps. I'm like talking through them rather than writing them out. And basically the way that I do these problems is the way I would expect you to. So there are a lot of times you can skip certain algebraic steps because they're obvious. Okay, so on the right, the 3's cancel. Then we have this cubic function. So I'll write it one more time. Okay, and then we take the cubic root. Okay, so this was our step 2. And then in our last step, I'm going to swap x and y. So I would have x equals the cubic root. Oh, I'm sorry, be y equals. Got to swap those. So y equals the cubic root of 4x plus 2 over 3. So your inverse function would be cubic root of 4x plus 2 all over 3. Okay. Visually, this is what's happening. So these graphs are better than what I can draw freehand. So the graph of f inverse is obtained by reflecting the graph of f in the line y equals x. So what that's telling us, if you look at these points here, A and B, and then you have A and B here. Well, an inverse just, if you have an X and Y value, and let's call the X and Y value 3 and 4. Well, then in the inverse function, those would just switch to 4 and 3. So that would be a point on the inverse function. So what that does, if you graph all of those points like that, you're going to just get this image that's in figure 9 here. So it's these two functions are inverses of one another, and visually, they're just reflected over this line y equals x.